So thanks everyone for joining us for today's webinar. We'll be introducing NRCan's heat pump selection app. My name is Jenna. I'm a Built Environment Initiatives Coordinator with the Community Energy Association, and I'll be facilitating the webinar this morning with support from my colleague, Terry McConaughey. I'm going to be giving a quick introduction, and then I'll pass things along to our speaker this morning, Rob Pope with Ecolighten Energy Solutions. Just the next slide there, please, Rob. Just forward in your slide deck there, please, Rob. Oh, perfect. All right. So I'm joining you folks this morning from what is now known as Cristova. It's a small community just outside of Nelson. It's been the traditional territories of the Snakes Nation, the Silks Nation, and the Tanaha Nation. And I just wanted to begin this morning by expressing my deep gratitude and respect for the generations of stewardship that allow us to enjoy these waters, rivers, lands, forests the way that we do. And as part of CEA's commitment to truth and reconciliation, I like to start these webinars introducing an example of Indigenous leadership in the built environment space. So here we're talking about Nisga'a Nation, and Nisga'a Nation is a self-governing First Nation on Canada's Pacific coast, primarily located in the Nass River Valley region of northwestern BC. Nisga'a Nation is working towards the ambitious goal of renovating 900 residential properties, aiming to update every Nisga'a member's home on Nisga'a land. To achieve this, the nation is building capacity within its government and community by providing training and government staff, nation members, and building trades workers. So collaborating with provincial industry leaders, Nisga'a Nation is facilitating the sharing and transfer of essential knowledge for projects. And this approach strengthens the skills and expertise needed to execute a successful retrofit program. So in support of this major retrofit initiative, the Northwest Energy Retrofit Forum was held June 3rd to 5th of this past year in Nisga'a Nation and Terrace, BC. Presented by the Community Energy Association and Canadian Home Builders Association of Northern BC, the forum brought together builders, contractors, building officials, and staff from local and Indigenous governments. Over 3 intensive days, they learned from BC's leading building science experts, looking at the issues affecting real houses in Lakalzap village and getting hands-on training in full-day workshops in Terrace. So if you're interested in learning more about the forum, please follow the link or the QR code at the bottom of the slide, and we will be sharing all these slides with you folks on the call. All right, and the next slide there, please, Rob. All right, so if you are joining us for the first time, a quick introduction to the Community Energy Association. So who are we? CEA is a registered charity and nonprofit. We're committed to accelerating bold action by local government and Indigenous communities. Oh, we are going way forward in slides there, Rob. Not sure if that's an accident. I'll let you, oh, we just went. That's okay. I'll give you a moment while you're getting that screen up on this slide there. I'll just continue introducing CEA. So yeah, as I was mentioning, we're a registered charity and nonprofit. We're committed to accelerating bold action by local government and Indigenous communities related to climate and energy. So we are the only nonprofit in BC focused exclusively on supporting local government and Indigenous communities on climate and energy activities. So what does that have to do with building better? Well, CEA's work, we recognize that the built environment is a main source of community-based greenhouse gas emissions, and that action in these sectors can not only result in significant GHG emission reduction, but can lead to enhanced resiliency and energy security while increasing the comfort, health, and safety of our homes. So CEA, we've been involved in building industry education and capacity building for almost a decade. And then on the following slide here, I'll introduce a few of our current projects. Perfect, thank you. So Building a Legacy North, Kootenay Clean Energy Transition and Retrofit Assist are examples of some of the projects through which we coordinate and deliver various activities supporting contractor capacity development across BC. So Building a Legacy North is a collaboration of CEA and Canadian Home Builders Association of Northern BC, and it focuses supports for the building industry and local governments in cold climates of Northern BC. The Kootenay Clean Energy Transition, or KCET, assists communities in preparing for a more energy efficient and healthy future by providing high performance building training and capacity building sessions in the Kootenay and boundary regions. And finally, Retrofit Assist offers a comprehensive concierge service to guide homeowners through the process of completing home energy retrofit projects with optional financing available. As part of this program, we do onboard retrofit contractors. So if you are a retrofit contractor, window and door installer, installation installer, heat pump installer, electrician, etc., working in the retrofit space. I will have some links in the chat that will give you some more information about Retrofit Assist. We run our program in Roslyn, East Kootenay, Kamloops, Whistler, and Squamish. So it may be of interest for you to check out. All right, and then a couple more plugs here and I'll pass things along quickly. If you are involved in the retrofit space, I just like to introduce the Home Performance Contractor Network. So if your clients are looking to access provincial and utility rebates for heat pump installations, window and door retrofits, or installation upgrades. So this is the network that enables your clients to access those rebates. So, and by joining, you'll have access to industry-specific training, and upon completion of the training, you may qualify for subsidies and reimbursements for course costs. So you can, if you have any questions about the Home Performance Contractor Network, you can reach out directly to their info at email address there. And then just a quick plug here for a new course, our micro-credential offered in partnership between the Home Performance Stakeholder Council, TECA, and BCIT. So this micro-credential is offered at BCIT, and it consists of 5 courses that introduce best practices and design considerations to ensure quality heat pump installations. So if you are an HVAC contractor on the call here, this may be a micro-credential that you're interested in exploring. So there's a link on the slide there, and again, we'll be sharing these slides out with you. All right, so just a couple housekeeping items and I'll pass things along. Just the following slide there, please, Rob. Perfect. So if you have questions for Rob, he's happy to answer them as he goes through. You can go ahead and type them in the chat. I'll be taking note of the questions that come through. You can also raise your virtual hand. If you look to the bottom of your slide there, there's a react button and you can select to raise your hand. The presentation slides and a copy of the recording or a link to the recording will be shared with you folks next week. And then if you're collecting CPD points, for those of you who are on the entire duration of the webinar, we will be sharing out a confirmation of attendance email to you in a few days. All right, so with that, it's my absolute pleasure to introduce Rob Pope, Senior Consultant with Ecolighten Energy Solutions. If you've joined us for an HVAC-focused webinar before, then I'm sure you're well aware of how lucky we are to have Rob here with us today to impart his knowledge gained through decades as an active member in the HVAC industry. And with that, Rob, I'll pass things over to you.
Thanks, Jenna, and thanks everybody for taking the time to attend this. I hope I make it worth your while. So this is Contractor's Guide to Heat Pump Sizing and Selection app. We're going to introduce the app. It's an Enercan app that is intended to be a tool for heat pump sizing and selection. This is, as I said, a tool, and it comes within the context of performance optimization with 4 key categories: initial considerations, heat pump sizing, heat pump selection, and control strategies. We'll go through each of those, and then we'll end with a case study example. And questions, of course, you can ask anytime during the presentation. I don't mind conversations. In fact, I like that. Okay, so why the Enercan Heat Pump Sizing Selection app is an important tool? That's a good question, because the issue is related to the high degree of, I wouldn't say failure, but the lack of optimization. Sometimes means failure, but there's a very chronic lack of optimization. So what that means is, reduced efficiency, shorter equipment life cycle, increased costs, and poor comfort. There's a process that we use to optimize a retrofit or a new construction installation. And what this tool does is help you with that. So the app is intended to support the HVAC industry with guidance. You don't need to use the app if you follow the process, but the app sure is helpful, makes it easier, whether you're a contractor, homeowner, mechanical installer. It's new-ish. It's been around for a little while, and it helps you select the equipment based on its database of equipment. So it has a really good database with performance curves, fan curves, efficiency ratings, and so on for a large selection of equipment. and it actually guides you through a process. And we'll share with you what that is. So first of all, project identification, details and options, air source heat pump unit configuration. That means, whether you're going to do a central unit or a split system and so on. Sizing approach and capacity requirements, existing constraints. Is the ductwork big enough or large enough? Is where can you put the outdoor equipment? How do you get the refrigerant line sets into the house and so on? House heating and cooling loads according to CSA F28012. That is a methodology for calculating the heat loss and heat gain of a building. And it helps you with heat pump selection, and also helps you with a bit of a cost analysis, utility rates, for example. And finally, with greenhouse gas emissions, cost and energy use comparison. So you can do a cost benefit analysis using this tool. So as you can see, you can do all this without it, but this makes it a lot easier. So there's 4 critical steps, as I said, that the app exists within. Remember, the app is there to facilitate this process, which is the process you need to go through to get the best outcome for that heat pump installation. So the initial considerations: homeowner interview, heat pump configurations and technologies, and potential project constraints. That's part 1 of the 4-step process. Heat pump sizing, so doing proper load calculations and calculating the balance point. And we'll go into why that's important a little later in the presentation. Heat pump selection, there's all kinds of them out there, and all of them have different efficiencies, different performance ratings, different capacities. So there's a little more to selecting the equipment than most people realize. And finally, control strategies. When does the thing turn on and off? What takes over? And so on. So it's thermostat settings, but it's also control of when your supplementary heat takes over, like your gas furnace or your electric strips. Okay, so initial considerations: homeowner interview, heat pump configurations and technologies, and potential constraints. We call this discovered because that's exactly what it is. You're discovering stuff. I think it's important. It's really critical, actually, because what we want to do is understand what the homeowner expectations are based on their research, what their friend told them, what maybe another contractor told them, and so on. We want to make sure that there's a reality check on expectations. We want to understand how their existing system has worked. You might find, for example, that they say, oh, that room up there, that's always been cold. Or that, the loft, it's always too hot. Or there's a big noise every time the furnace comes on. You can get an idea of the existing system's performance so that maybe you can correct those issues. But it also, if you're a mechanical contractor, gives you some insight into the distribution system. Motivations. Why do you want a heat pump upgrade? It might be just simply that the old furnace crapped out and you need something now, soon. Or it might be part of a more calculated strategy to improve the efficiency, lower your GHGs, improve your operating costs, and so on. So it can be anything from one end to the other end of that spectrum. It's good to know what the motivations are. And of course, as I said, expectations and concerns. What's it going to look like? Where's the outdoor unit going to go? How are those refrigerant lines going to travel from the outdoor unit to the indoor unit? Is there any changes I need to make inside the house, and so on? So it gives you an opportunity the discovery that is, gives you an opportunity to understand the existing system, the motivations, and the expectations, get all those things aligned so that you can develop the beginning of your strategy for going forward. And there is an appropriate heat pump configuration and technology for every retrofit. They're centrally ducted, all electric, centrally ducted dual fuel, ductless single zone, ductless multi-zones, and ducted concealed systems, and maybe a combination of some of these systems. And as far as technologies go, you can get a single stage, which will be the lowest on the capital cost side of things, most affordable, but the lowest efficiency and lowest comfort. Now, as you can see on the graph on the left, you look at that red line, your single stage heat pump is going to overshoot the set point on your thermostat, and it's going to undershoot it, go way down and way up and way down. So it's like going between red lights and hammering on the gas, and then hammering on the brakes, and hammering on the gas, and hammering on the brakes. It's not the best way to go. You want to cruise like that gray line, and that would be either your two-stage, but more likely, more effectively, the VRF, variable refrigerant flow, sometimes referred to as VRV, same thing. The difference between the single stage and the two-stage, and I remember when the two-stage came into the market, I was installing back then, we thought, okay, this is it. This makes all kinds of sense. This solves all the problems, right? We don't need the full capacity all the time, especially the long shoulder seasons. We only need some of it, and the two-stage addresses that problem, and it makes it a little quieter and a little more efficient. Then the variable refrigerant flow came along. Oh, geez, okay, this really takes care of it because it actually modulates itself. It's kind of based on demand. It's capable of, it's like the difference between the drive between Vancouver and Calgary going through the mountains compared to the drive between Calgary and Winnipeg in a straight line, flat. You're going to have much more efficiency, much more comfort too, because you don't have the same amount of cycling as you would with a staged heat pump. And there's a few other things you can do with it. You can have one outdoor unit and multiple indoor units because of its modulating ability, which is really handy. In this first stage, pre-change up, one of the things that we want to do is understand the ductwork. Can't emphasize how important this is, because if you're just guessing, you're probably going to run into a problem with the sizing of the ductwork and the amount of airflow that the new heat pump needs. It's a very fine line. It has a very specific need for airflow crossing that coil. And ductwork tends to be undersized. Not always, but that is the general trend in most existing systems. So you got to check it. You got to see how much static pressure does this ductwork system have. And that can only be done if you measure it. And you have to measure it. It's due diligence. If you don't, you're just guessing. So you want to do a static pressure test and see how much capacity that ductwork has for the intended new heat pump, and whether it'll work or not, or if you have to do modifications to make it work. The airflow impacts the size and the performance of the heat pump. It effectively impacts the choice of the heat pump too, for that reason. Centrally ducted heat pumps, as I said, have very specific requirements for airflow, and the ducting has to be able to handle the size of the system being installed. Calculate the possible airflow range to select the optimal heat pump size. So that's another critical thing. So you've done your discovery with the client. this is the next thing you need to do is see, what your restrictions are, if there are any, and what your opportunities may be. Electrical panel, this is a big one. An awful lot of retrofits have small panels, so you really have to check it. You can't promise that you're going to put in a 3-ton heat pump where you just had a gas furnace and there's, you don't have enough electrical capacity, or you don't have the physical space on the panel to put in that breaker. So you got to check that. You get a low service, less than 100 amps. It's not unusual. Here in Vancouver, there's a lot of houses with 60 amp services. Maybe there's too few breaker slots, in which case you have to change the panel. Maybe damaged slots in an old panel. But there's usually solutions: replacing the electrical panel or disconnect items where they're no longer needed. So if you had electric baseboards, electric heating, you don't need that anymore. Now you got a heat pump. Take those breakers out, and then that'll give you room on your panel. Or you can use an energy management system to connect additional loads without increasing the service. So basically what that energy management system does is it prioritizes your loads, so you don't have them coming on at the same time. So there's a process there. Sometimes it'll take an electrician to understand it. Either way, that has to be sorted before you go any further. So you've done that. So let's just go back. We've, done the discovery. We know that we can put a heat pump in any situation, some sort of configuration. We figure that out. We choose the technology, and we test the ducting, and we check the electrical panel, and then we have completed steps 1 through 4 in the app. Initial considerations. Section 2, heat pump sizing, which includes load calculations and the importance of a balance point. So load calculations, the methodology, the approved methodology, the CSA F280-12. That methodology is actually embedded in the building code, section 9.33.5. It's the only compliant software or methodology. There's several types of software that uses that compliant methodology. Using this standard for load calculation does a few things. It ensures that the system is going to be right-sized. It ensures comfort, and it ensures reduced installation costs, and it also reduces your liability risks. If you're not using this and you're just guessing, and it's a coincidence if it's the right size, it's better to calculate than to simply guess. Very critical. There's we do an awful lot of third-party interventions, where something's gone wrong, and we get asked to come and have a look and see if we can sort it out. And a very large portion of the issues is related to equipment typically being oversized, occasionally undersized, but almost always oversized. And that has all kinds of implications: short cycling, shorter lifespan of the equipment. It's off and on, off and on. So of course there's noise and comfort issues with that. And operating costs. Plus, you probably didn't need to spend that much money on a bigger system in the first place. So there's no real upside to oversizing, but there are a lot of downsides. So there are 2 basic types of load calculations, both using the F280. One is a block load. Block load is typically used for energy modeling and for retrofits in existing homes. Room by rooms is required and is needed for new construction. You need to do each room's load independently. But for retrofits, you just need to do the whole house, unless they're opening up all the walls and ceilings and they want to make some other changes in the house and it's a deep house retrofit, then you may want to do room by room to more customize the system if you have the opportunity to access the ductwork and modify it. As I said, CSAF 28012 is a methodology. It's an approved methodology, a very prescribed methodology, a CSA standard. But there are a number of softwares that are available to users, contractors, designers, and so on, that has been verified to qualify as an approved software using the standard. TECA, which is the industry organization in BC, has a very accessible, inexpensive software tool that you can use. That it doesn't have a steep learning curve. It's very, very effective. RightSoft, that's also really good. It's just it costs a little bit more. Excuse me. It has a higher, steeper learning curve, but it does an awful lot more than just your load calculations. It's a design tool. It's a really cool one. We like it a lot. HeatCat is similar to RightSoft. It's used quite a bit by contractors for radiant and floor radiant primarily. And there's also software called VoltaSnap. Now, what VoltaSnap does, it takes something that has to be done anyways in a lot of cases, which is an energy model by an energy advisor, done in a program called Hot 2000, which is a modeling program from Intercant, which is not F280 compliant. However, VoltaSnap takes the inputs from a Hot 2000 model, something that's already been done, all the legwork's been done, and it converts it. It does the math behind the curtain and converts it to make it compliant with the CSA standard. So those are a few options. So balance point. The balance point is the outdoor temperature at which the heat pump no longer has the capacity to keep up with the set point demand. So basically, it reaches a certain temperature and it can no longer keep up. You need something else to take over or assist. There's a capacity balance point. That's the outdoor temperature, which the primary heat from the heat pump doesn't have the capacity anymore to deliver the heat. There's also an economic balance point. That's the outdoor temperature at which it's more cost effective to go to your auxiliary heat or your supplemental heat. So there's two balance points, the capacity balance point and the economic balance point. Across the country, that economic balance point varies depending on the cost of energy, the cost of electricity, cost of gas, and things like that. In BC, it's pretty uniformly better to go with the capacity balance point because of the cost of utility like natural gas and electricity in this province. The balance point is calculated based on the fact that heat pumps tend to drop in their capacity and their efficiency as the outdoor temperature gets colder. I'm sure everybody knows that. So excuse me for pointing that out. But they're all different. Every single heat pump out there has got a different performance curve. You know, some of them are flatter, some of them are steeper. Every home is unique in where its load calculation is. So you have the uniqueness of the proposed heat pump performance curves and the uniqueness of this particular home's load, heating load primarily, and then depending on the location, what the outdoor design condition is. So if we look at this one here, we can see There's the heating load curve. All right. We at about 60 something degrees Fahrenheit, just around, I think, 18 degrees Celsius. We don't have a load. At the design condition, we have, which is 25 degrees Fahrenheit, whatever that is Celsius, I don't know, 17. The load is somewhere around 15,000 BTUs. The heat pump starting point is 47. By the way, that's the starting point for all heat pumps. That's the starting gauge. All heat pumps are a 3 ton, 4 ton, 2.5 ton, 1 ton, or whatever at that temperature, that outdoor temperature. And then when you leave that temperature and you start going down in outdoor conditions, that's when they all, take their own path and have different performance curves. And in this case here, this particular heat pump, as you can see, it drops off. And there is the balance point, D. If you can see where that is. Sorry, I gotta move something out of my screen here so I can see what I'm looking at. So the heating load at 99% is A. The heat pump heating capacity at 17 degrees is B. The heat pump heating capacity at 47 degrees, that's its starting point, is its nominal capacity, not its effective capacity. And the balance point is D. And that means that everything after that is where you need to consider your options. Whether you're going to resize the heat pump to take care of the whole load, choose a different heat pump that can do that, maybe a cold climate heat pump, or a heat pump that has auxiliary or supplemental heat. If it is an all-electric system, it will be electric strip auxiliary heat. And in this case here, as you can see in the red arrow there, it's about 2 kilowatts is what you need for an all-electric system. So what will happen is when that heat pump reaches the set point or the balance point, you'll keep going, but it'll need that extra 2 kilowatt electric strip heat to assist it. If it is a dual fuel or hybrid system, when that heat pump reaches that balance point, the gas furnace will say, okay, I'm going to take over from here. You'll need that gas furnace to be able to do the full capacity, in this case, approximately 16,000 BTUs. You'll have to take over completely.
Rob, just a little clarification on that graph there in the chat. Meredith just wanted to clarify that the graph says that after 25 degrees Fahrenheit, or actually it's minus 3.9 degrees Celsius, supplemental heat is needed.
Yeah.
Perfect. You understood correctly.
So the diligence required is that even within the same manufacturer, the same brand of heat pump, different models will have different performance curves. Every brand is different. Within the brands, the models are different and the sizes are different. So you got to look it up. You got to check it. And it's easy to get at. It's not, you have to dig hard for this information. It's very available, but you got to do it. And what that means is there's no such thing as a universal balance point. You'll hear it's said very often, you need it to go to your supplemental heat at 5 degrees Celsius, or 3 degrees Celsius, or 1 degree Celsius, or minus 5 degrees Celsius. None of that is true. It's a coincidence. If it is, it's based on the heat pump. They're all different. They're all different from each other. So we've done step 5 now on that tool. If we've done these things, which is the load calculations, right? The balance point, check that out. And we've chosen the equipment based on those things. And the load calculations and balance point. Step 5 of the tool is done. Remember, it's a tool. It actually prompts you through. You just asks you for information. You put in the information, and then it gives you an output that you can use to go to the next step. And in this case, the next step would be heat pump selection, capacity and efficiency, and supplemental heating needs. As I said, the performance specifications of equipment varies from heat pump to heat pump to heat pump. The Enercan heat pump sizing and selection app is a tool to support contractors with performance data to make informed decisions. So unlike me, for example, where, I've done this so often, I have a database already of all the equipment. I know where to go to get the performance data, fan curves, and all that kind of stuff. If you don't have all that behind you, you can simply use this tool. In fact, it's easier for me to use the tool because all this information is very available within the app. Handy, a very handy tool. Just a note on cold climate heat pumps. Remember, I was speaking about the evolution from the single stage to the 2-stage to the variable refrigerant flow. Well, in the recent years, they've been around for a while, but relatively speaking, cold climate heat pumps are new-ish. So they take the VRV technology, inverter-driven variable speed compressors, and they adapted the technology in those so that the heat pumps, cold climate heat pumps specifically, can operate down to minus 15 degrees, sub-zero temperatures, Celsius that is, and go even as low as minus 30 without significantly losing its capacity or its efficiency, I should add to that. It can meet a higher heating demand, but it also comes with a higher installation cost. So you got to kind of figure out whether it's worth it or not. In almost all cases, it's worth it. Even in climate zone 4, which is a lower mainland, relatively mild climate compared to most others, we use cold climate heat pumps because then we don't need any backup. And here is a solution to panels that are very small, a 60 amp panel. The biggest draw on the panel is electric backup, for example. If you don't need any, a cold climate heat pump will do the whole job. In colder climates, we put these things all over the province and every climate zone. And this is one of the few products in this whole industry that actually outperform the manufacturer's hype. It surprises us how well they do. And this isn't just one product, this is a variety of products. When we talked about auxiliary heat or supplemental heat, you'll often hear the term backup heat and emergency heat. We have to be careful that we distinguish these terminologies from each other. Auxiliary and supplemental heat is the additional heat that you need to have when the heat pump isn't able to keep up with the demand, usually during peak load conditions. The terminology should not be confused with backup or emergency, which is a heating source that you have in very rural areas that are not close to access to suppliers and contractors to fix things when they go wrong. This is where you want your backup system or emergency heat. They'll take over if something happens to the primary heating system, your heat pump. So with that, the heat pump selection, we're going through the capacity. We're choosing the technology. And we are determining the source of backup or auxiliary, or supplemental or auxiliary. It could be a gas furnace, or it could be an all electric system with electric strip. And in some cases, excuse me, and this is actually, believe it or not, really close to Vancouver, big city. We have communities that, for example, where I brought my family up on Bowen Island, 20-minute ferry ride from Vancouver. You want to have backup there, in places like Lions Bay or remote places up there. Once you get out of the Lower Mainland, there's a lot of them where access to a supply chain is limited and access to technicians is limited, but backup is a good idea. Heat pump selection, stage 6. Capacity and efficiency, supplemental heating needs, balance point, prescriptive outdoor temperature. Sorry, we've done step 6, which we just talked about. And now we're going to step 4. Balance point, prescriptive outdoor temperature. It's pretty important when we talk about control strategies. And it's not just about your thermostat, and where to set it and how to program it. It's about when your supplemental heat comes on. It affects installation costs. For example, if you can get away with a cold climate heat pump, you spend a little more for your heat pump, but then you save on that electrical panel upgrade, for example. Saves on operating costs. You want to use whatever is most efficient, and in most cases, it's your heat pump. As much as you can, you squeeze as much of your heating needs from that heat pump as you can, and that will give you the best chance of lowering your operating costs to its optimum. And comfort. You don't want something that's oversized off and on, overshooting the set points. And obviously you want to stay warm when it's cold. It's important for competitive pricing. Of course, customer satisfaction. You don't want unhappy customers. Energy management and environment. Of course, the more your heat pump is on, and the less you use your gas backup or supplemental, the less GHGs you use. So we use the Intercan tool on a detached home and cam loops to look at different approaches. There's 30,000 BTU heat loss, minus 23 winter design temperature with a heat pump capacity of 2.5 tons. And this is really interesting. So here's the all electric heat pump balance point chart. So the capacity of the heat pumps, there is that orange line. The heating load is the blue line. And there's the balance point at minus 11. And in this case, we need a minimum of 6.5 kilowatt of auxiliary electric heat. Okay, so let's look at dual fuel. This is with gas furnace. So this is a gas furnace with a heat pump coil in the plenum. Heat pump is primary. Gas takes over after the balance point. You need the whole capacity, 29,000, let's call it 30,000 BTUs. Okay. This might look a little complicated. Bear with me here. So you can see the heat pump in cooling mode is in the blue at the top. Heat pump in heating mode, most of the time, almost all the time, it's in this range. The heat pump is doing the work, right? And the auxiliary heat, for example, gas furnace, is only on for a very small period of time. This is at the balance point of -11, right? Okay, now let's look at this. We use a prescriptive temperature, 3 degrees Celsius, for example. Even the BC Housing has a artificial balance point. I can't remember what it is. I think it's +5 or something like that. But whatever it is, you're better off with the actual balance point than a prescriptive one, because look at the difference. Now we have all this extra time spent in auxiliary. Now we're using our auxiliary heat at a higher cost and higher GHGs. Whereas if we just had, let's go back here, just use the actual balance point, that heat pump doing most of the work, we would be much better off. So see how much of a difference it makes. This is actual data from an actual installation. Okay, so that's step 4 completed. By the time you get here, you've done the whole app. Remember, the app prompts you through all of these steps. It is helping you go through a very critical process, the journey of a heat pump installation for a retrofit. These things have to be done whether you use the tool or not. The tool just makes it a lot easier. We have a bit of a case study here. It's home in Burnaby, built 1980, about 2,600 square feet. It had an existing mid-efficient gas furnace, 70,000 BTU input. That meant 56,000 BTU output. And it covered 100% of the heated floor area. You look down below and you can see that the actual load is only 33,362. So just changing, doing a load calculation and changing the system by itself is going to save money. Static pressure test was done, and the simple fan law calculation based on the CFM of the new equipment will show that the static pressure of the existing ductwork system with a new higher CFM. So basically we're saying, okay, let's see how much air can go through this ducting system at what static pressure. And in this case, we did the test, and you could see that 980 CFM goes through that ductwork at 0.5 inches water column of static pressure. That is pretty typical. 0.5 is kind of a standard. It's not for all systems, but it's a good place to start. 0.5 inches of water column. So we know we're capable of 980 CFM. Now we want to choose a heat pump. Remember what the heat loss was. Just over 33,000 BTUs. In tons, that's just under 3 tons. The heat pump that we would want is 3.5 tons. That requires 1,400 CFM. That would, in that particular ductwork, far exceed the 0.5 inches water column. It's about double the static pressure. So what do? Well, there's a few options. Ductwork modifications to reduce the static pressure. It's surprising how often that will work. You think you've got a furnace stuck in a closet in a basement, no room, everything else is concealed behind finished walls and ceilings. What are you going to do? Well, there's often things you can do. So you almost always, these furnace rooms are adjacent to halls or other rooms where you can put more runs, more return airs, especially. They're typically return airs are the problem. There's not enough in most cases, and particularly at the lowest level of the house. If you can get a return air right next to that part, through the partition wall between the furnace and a hall or another room, low, close to the floor, that might help. The other thing you can do is put a bypass. So you can put a bypass between the supply and the return air, and that will cheat the system into thinking that there's not that much pressure. The other thing you can do is do a dump zone if you got a crawl or an attic, or even the furnace room itself if it's big enough. What you do is you take a pipe, you essentially pipe it off the plenum into the room, and you put a little bypass damper in it, and it's not that expensive to do. Set it, and when the pressure exceeds what the capacity of the heat pump wants, you'll release that pressure into the room and everybody's happy. So there's a few things you can do to modify the existing system. That's not the things that I just mentioned is not all, there's other things. Another option is instead of a 3.5 ton, we put in a 2.5 ton heat pump, right? Central. And then we put a remote ductless heat pump somewhere else in the house. We still get the total capacity we need, but we're not trying to push it all through that same ductwork. That's another option. Another option is reduce the heat pump. Don't put a heat pump that is trying to do the full capacity, and supplement it with electric resistance heat. So there's options. In this case, I think what did we do here? We went with the 2.5 ton heat pump, I think, in this case, in a ductless. The key learning, number one, Intercan's air source heat pump sizing and the selection map is a fundamental resource. It supports a more effective approach to equipment decision making. Remember, it supports the process. The process has to happen. If it doesn't, you're really vulnerable. It's actually the homeowner that's very vulnerable for the outcome. Better data is critical to avoiding performance issues and callbacks. Code compliant F28012 load calculations are the foundation on which all other HVAC decisions are dependent. Don't do those. Everything else has a potential to amplify potential failure of the system. Contractors should avoid the risks with improper sizing based on rule of thumb. Rule of thumb days are over. It used to be okay, but nowadays it's not okay. A rule of thumb calculation in a retrofit situation is, to me, a big red flag. Get a different contractor. Don't do a rule of thumb. Control strategies. And you can see from the balance point data that we had on that house in Kamloops that the balance point makes a big difference, right? If you adjust that balance point, you adjust a few other things. You adjust performance, you adjust cost, operating costs, you adjust comfort. So what you want to do, as I said, in BC, you want to, from both a thermal balance point and an economic balance point, it's best to squeeze as much out of the heat pump as you can. That is your most efficient piece of equipment and has the lowest carbon footprint, and it's going to give you best operating costs and comfort. To achieve optimal heat pump performance, a comprehensive approach is required. These are the 4 steps we went through. You need to do the homeowner interview. You need to know what they want, why they're doing it, what information they already have in their head, whether it's real or exaggerated, or, because anybody can Google anything these days, or somebody tells them, oh, you got to do this, got to do that. You want to make sure that there's a reality check on the expectations. You need to do load calculations, ductwork evaluation, and you need to understand the heat pump options. That's the performance curves. Doesn't take much to look them up. By the way, while you're there, look up the fan curves, because in some cases, like that case with the 0.5 inches water column on that case study, you might be able to find the equipment that has a higher tolerance for static pressure. Some equipment might go up to 0.8 inches water column, for example. right? And you might be able to, choosing that equipment, get more capacity performance using the same ductwork. It's another solution. So it's performance curves, fan curves. In other words, contractors should do their homework and auxiliary heating needs and strategies. This is all part of the journey to optimizing a heat pump installation. And that's the slide we were all looking for. Thanks. You got any questions?
Wonderful. Thanks, Rob. All right. Sounds like a good tool to make sure that we're checking all boxes while selecting that heat pump. So thanks so much for taking us through that. We did have a couple questions come through the chat, and folks, please continue to put your questions in. I'll do my best to answer them all. And if I've missed you, please let me know. There was a question or more of a comment that I thought maybe you might have a comment on as well, when you were talking about looking at panel sizing, the very beginning of the presentation. Someone suggested using historical load calculations as per Technical Safety BC rules. So looking at the historical electrical use of that panel. So just
Yeah, yeah.
comment there.
There's no, that's a good point. Yeah, and I think that, as you know, I mean, everybody's got their hydro bills. It gives you the usage between billing periods, and you might discover, you've got a 100 amp panel. There's only so many circuits being used on a regular basis, so much amperage being drawn, based on your historical data. That's one thing. I mean, you got to do the physical. Is there enough breaker room on the panel? Period. Is it an old panel? Will you used up every breaker? How much of these breakers, if you've got a few plugs on one breaker, you could, bundle them together on another breaker. You're still within the 15 amp range. There's a lot of things. I mean, it's not rocket science, but in a lot of cases, you might want to get an electrician to do that evaluation, unless it's extremely obvious one way or the other.
Yeah, great. Thank you. And I did put a link in the chat there in response to that question. We held a webinar on that topic of using historical data. It's geared towards community and homeowners, but if this is a new topic for you, it might be of interest to explore. Let's go ahead and have a look. All right. Ashley asked if the case study, the Kamloops case study, sorry, was it Burnaby? Sorry. The case study is available anywhere with greater detail of the process and final solution.
If Ryan's still there, he could answer that.
I thought you might call on me. That's just a theoretical, actually, that's just a theoretical case study. Like the follow-up slides that we had that we took out just showed various load profiles and graphs, but it wasn't an actual like implementation at a home. It was more just like, if we had these constraints with the ductwork, what would be your options for proceeding depending on the homeowner needs and objectives. But happy to chat with you about it if you want to reach out to me or Rob.
Thank you.
Great. Thanks, Ryan. All right. If there is no universal balance point, maybe you don't know this, but why does Clean BC Home Renovation Rebate Program require a set balance point of 5 degrees Celsius for homes in the Lower Mainland and 2 degrees Celsius for the interior for the dual fuel systems?
Because it was a bunch of bureaucrats that figured that out. Seriously. I mean, it makes no sense. They had to come up with something they figured.
Minimum.
And and they didn't want to burden the process with, you got to do load calcs and all this kind of stuff. It was the usual stuff. But it's, ignore it. It has no real value. And there's no such thing.
Yeah, the more nuanced answer would be they had to set up a minimum requirement for what they wanted heat pumps sized for. And so recognizing the fact that actually doing balance point calculations and looking at performance curves and load calculations and using the that type of methodology to customize it based on the house is a place where industry just isn't at this point. But that's where we need to get to. So
Yeah,
that was the happy, I guess, the
And-
happy medium for whoever asked that.
the reality is the
question.
industry is evolving in a good way. And there are an awful lot of contractors all around this province that I deal with on a regular basis that do their diligence, and they're very, they're very motivated to provide the best service possible. And more of those contractors in the province are becoming that way. It also gives them a competitive edge. But probably at the time of the policy, there was less of them. And, be honest with you, I said before, it would have been better to require the due diligence in the first place. So this is what homeowners are entitled to. They're the most vulnerable part of the chain. And the reason there are so many failures and expectations not being met is because that diligence isn't done. And so that should have been the priority, but it wasn't. So I would just ignore that. It's not realistic.
Well, just one other thing I would add is somebody brought up in the chat a situation. I don't know if they're an EA or whatever, where they went out to a house where the switchover was at 12 degrees C. So that effectively what they're trying to do was, or what they are trying to do is to put some guardrails on the sizing of systems so that they are operating not just as a cooling device, but providing appropriate space heating. And hopefully optimized, as Rob's talking about. There are contractors who are looking at sizing it and selecting it so that it can optimize throughout the heating season.
Because it's a max temperature for the turnover, right? The 5 degrees and 2 degrees.
Yeah, it has to be able to deliver at that temperature. Like, that doesn't mean it has to be sized to there. If you can make the heat pump larger and it works with the ductwork and it's able to service the house, then, obviously go further, right? But they don't want it to be sized for switching over at 12 degrees, right? Where it's, basically running at minimal shoulder season and used for cooling. Anyways, we're down into the weeds now.
Great, thank you. And Stefan, I see you have your hand up. I'm not sure if it's a comment to this discussion or if you have.
It's a comment to that.
Sure.
The wording is actually rebate driven, so you cannot get rebates if it's 5. If it's more than 5, if the set point is set to more than 5, it actually says in the wording maximum 5 degrees. You can lower it, but for some reason the industry has now, or some people think now 5 is the magic number, and that's even in the rebate wording, it says maximum. So, but it got very confusing.
Mm-hmm.
It got very confusing. It's now kind of like the magic number in the Bible for setting it, and that's entirely wrong.
Yeah, everybody thinks 5 and 2. 5 and 2.
Okay, well then, thanks for the question. I hope that we've at least cleared that up for a few of you folks on the call. Great. Just as we go through, if you've joined us for a webinar before, you're familiar with this process. As we go through this Q&A portion, I'm going to start a feedback poll just so that we can hear from you folks on the call, what you thought, what we could do better next time, what you enjoyed, and topics for future learning opportunities. We do take into consideration everything that we hear from you when we plan out future sessions. So you'll see a pop-up on your screen. Please take a couple minutes to fill that out. All right, just moving on to our next question here. Shane asked this. I know, thanks Casper for answering in the chat, but just for folks who will be watching the recording or maybe not keeping an eye on the chat, I think it's an important question. If cooling capacity is higher than heating capacity in the F280 12 calculation, which do you size the heat pump to?
With all other things being equal, in other words, you have the ducting capacity, available. I size for the dominant load. The critical thing to keep in mind is, especially with new construction, as houses are becoming better at keeping the heat in, the higher energy performance homes, the cooling load tends to become dominant. In any case where the dominant load is cooling, you have to size to the cooling, because you can't make more cooling, whereas you can make more heating. You can supplement or create auxiliary heat. You can't do that with cooling. So you want to meet the total cooling load, unless there is some other reason that is not a priority for the client.
Great, thank you. All right, and Casper asks, how can we tell that a heat pump is variable capacity? So he has seen cold climate heat pumps that are listed as single staged or two staged, and he thought that the implication was that cold climate heat pumps are all variable. Is there?
Yeah, we have to be careful. I mean, there's a bit of complication there, because even a variable capacity piece of equipment has speeds, has variable capacity within set ranges, right? It's still load matching. That's what the heat pump's doing. It's still load matching. It's still ramping up and down based on load. It gets sensory information from inside, and opens and closes the expansion valve, and according to the need, and ramps up and down according to the need. It's still variable, but it's just within different speed ranges.
Great, thank you. All right, that I believe was all of the questions in the chat, folks. If you have, if I missed a question, just pop it in the chat again or raise your hand, and we'd love to hear from you. If you do have any other questions, you can go ahead and pop them in the chat or unmute yourself. I was wondering, Rob, that slide you had, it was the cam loops, and you were talking about the balance point versus a set point. Was that graph from the app itself? Like, is that a visual from the app itself?
No, I think that is from the data logging that was done for that particular one.
Okay.
So that's the actual performance. Am I right?
Yeah.
Yeah.
Yeah. So the old Excel worksheet that they had that was pre development of the app used to be able to produce those types of charts and graphs with run times and stuff like that. But the app doesn't do that.
Okay.
Can I add something?
Yes, go ahead.
Maybe Rob and Ryan can comment on that as well. I'm not sure if the app is asking for what future plan or retrofit plans the homeowner has, because if, for example, the windows are due in 5 years and you get a heat pump that's essentially then 25% oversized because the heat loss is much less in the foreseeable future, that should be definitely something that the heating contractor should at least be aware of, or talk with the homeowner about what's your plan here, because we'll encounter a lot of short cycling otherwise.
Yeah, you're absolutely right. If you're doing especially a deep energy retrofit of the whole house, the furnace that you put in for today's house versus the system that you would need for the house after the retrofit, you'll have put in an obsolete system that's going to be obsolete or far too oversized. So that's part of the importance of discovery, is to find that out. What's the and if there are plans to seal the house up, put in extra insulation, or whatever it is, it's important to know how committed the homeowner is to that and the timelines, and make the homeowner aware that that it matters, because that'll determine what capacity we put in now and for how long that capacity will be appropriate.
But also that's a good way for investing in variable technology with a higher turn down, right?
Yeah,
Like that's where they can steer them, like maybe slightly oversized, but ability to turn down.
yeah, yeah, to a degree, yeah.
Yeah.
We did some case studies on house where the deep retrofit, that the straightforward switch over from the existing system to a new system was fine. A light retrofit where you're just blowing in some insulation, changing the windows was fine. That same unit you could modulate and vary to both those situations. But when you got to a deep energy retrofit, it would have been obsolete. So it really does matter. You really do need to get informed and find what the level of commitment is over what period of time to what level of retrofit for the house itself.
Yeah, I would. I'm not sure who asked that, but I can give a quick plug. The fall sessions, Jenna, that we did on dual fuel, part 1 and part 2. There was, I think, part 2, we had a good case study that went through different upgrade packages and what that meant in terms of system sizing and selection. So if you're interested, that's a good place to have a boo at something.
Yeah, that's the one I was thinking about. Yeah.
Yeah, perfect. I'll put the link in the chat to all of our previous webinar recordings so you can find
Good
it
question,
there.
though.
Thank you. I'm not sure if you want to comment on specific manufacturers, but Jay's just asking for your comment on Midea heat pumps versus Gree heat pumps, as they seem to be the main manufacturers.
Which heat pump versus Gree?
Midea, M-I-D-E-A.
Oh. This is a tough question.
Yeah.
It's really hard to provide a qualitative answer to what manufacturers, because so much of the performance of the heat pump is about how it's installed, the process it went through, all the things we just talked about, gives whatever heat pump you put in the best chance of performing well. There are products on the market that lead in terms of technology, quality, and performance. They're usually more expensive. They're like Mitsubishi, Daikin are a couple of examples. There are products on the market that have a reputation over a long period of time of, poor manufacturing or assembly. They're the kind of products that, back in the day when I was installing, servicing, troubleshooting systems, tools on, you'd see a product and you go, oh no, there's chronic issues with some of those products. I also understand there's a very high deference that has to happen to budgets. What can you afford? That really matters. And sometimes going to the product that's not quite as robust as some others is the appropriate choice because of the budget restraints. Real life situations, budget being one of them. So I can't say that the one product is better than the other. I can tell you this, that when we can, we prefer on the cold climate and the variable refrigerant flow systems, Daikin and Mitsubishi, the Japanese technology superior. They lead it. When it comes to domestic products for gas furnaces, for example, and matching heat pumps, which is pretty important to match your heat pump to your air handler, whether it's an all electric system or dual fuel system. We think that there's a few major brands, Carrier, right? They're the same. American Standard, Trane, they're the same. Lennox, they're all good brands. Depending on the model, every brand has your, budget models, your best and better. models. So much of it depends on the on how you prepared for the installation and the quality of the installation. So much of it depends on that. Part of it depends on the quality of the equipment. And that is dependent on a lot of things, and then budget, availability, contractors' relationship with the supplier, manufacturer, and all those kinds of things.
Rob, I just threw in the chat the LEEP database, which is a great place to like compare different manufacturers agnostically, based on like performance curves and things like that.
Yeah, so that's the on paper stuff, right? So you can look at 3, 4, or 5 different brands and see which has the best
Exactly
efficiencies and so on. But what it doesn't tell you is which has the reputation for the most maintenance requirements, repair requirements, and that kind of stuff. That just comes with, you really want to know about a product. What you do is you go on Google and you search HVAC forums. And that's where you really get good, real information, mostly from mechanical technicians who deal with the stuff every day, and they back and forth online about this or that product, this problem, that problem. And that's where you really, other than your own experience, where you see what's actually happening in the industry.
Great, thank you. Great tips. All right, this is a question about measuring static pressure. I'm going to do my best to ask the question to you directly, but let me know if I need to repeat anything. So it's asking if the measured static pressure for a set of ductwork needs to be overcome by the fan of the air handlers. So the example you had 950 CFM at 0.5 inches water column measured. When selecting the equipment, if it can output to 0.8 inches water column, does that mean it can push more air?
Yes.
Great.
Yeah. It has, yeah. I mean, there's a variety of, like, there's a lot of concealed fan coils that have extremely low static pressure tolerances. These are the ones you hide in ceilings and stuff like that. They're still ducted, but the ducting is intended to be short. Usually the room adjacent to maybe a couple of rooms. And they have extremely low static pressure tolerances. And then there's mostly the central. A lot of brands will go, even there's some that even go up to 1 inch water column. They just have the fan capacity to overcome the static pressure. It'll deliver the CFM you're asking for, depending on the fan performance curves. That to me is a pretty critical. When we're designing systems, we look at first we know what we need to deliver to each register, and add that up. And okay, we need 1400 CFM or whatever it is for this system. Okay, let's look at the equipment fan curves, which can do this, which can't, based on the static pressure of the design system. The fan curves are pretty important, and that is not quite as ranging as performance curves like capacity and efficiency, but there is quite a bit of variability between one product and another product. And so it's helpful to understand what the performance curve is. But that means nothing unless you've done your pressure test in the first place.
Exactly.
Great, thank you. All right, we have a couple other questions here, folks. If you have other questions, feel free to continue popping them in the chat. Richard asks if heat pumps in general are now being developed with lower costs in regard to cooling needs, or if they're all the same when it comes to meeting the heat dome type events that we're seeing cost-wise.
Well, meeting the heat dome events is a design
question.
Yeah, because you're designing now for heat dome events. It's not the equipment itself that is capable of doing that. You have to choose in a heat dome. What do you choose? What extreme temperature do you choose? It's real guesswork. I can tell you this though. We had that heat dome in Vancouver, where incredibly a few years ago, it reached 40 degrees Celsius, which is unbelievable, in Vancouver. It was crazy. And I remember that happened on a weekend, and that weekend I couldn't sleep. Besides the fact it was hot, but I was worried. I was thinking, oh no, the phone's going to start ringing. What's going to happen Monday morning is going to be, oh my God, but nothing happened. It was a non-event. And what it made me realize is that the F28012 calculations that we use, remember, we have thousands of customers out there. The F280 load calculations that we use have built-in resilience, for one. And secondly, if you come to a situation where you need 3 tons of capacity to do the job, right, and that's right on the line, you go to the next size up that builds in extra resilience. And one other little tip, and this is something that I have discovered over time, is we look at climate data that is published in the BC Building Code, and it is old news. You can easily, in no time at all, seconds, get actual data for the last 5 years. In any place you can go town by town, region by region, right, in any climate zone, and find what the actual data is for the last 5 years. And that is more important. And if you look at that, you'll almost always bring your outside design temperature in the winter up in the summer. If the BC code says designed for 28 degrees Celsius, you're wise if you design for the data that's been available for the last 5 years, which will usually bring it up to, say, in Vancouver, for example, we designed at 31 degrees Celsius. So that builds in resilience. There's a bit of common sense that you need to apply. And one of them is don't use old data, use new data. It's so available. Why not? It just gives you the build. So that's the resilience part of designing systems is for those future heat conditions. And especially if there is retrofits done to improve the energy performance of the house itself, then you're building a house that is just much better at keeping heat in. And you're increasing the internal gains are still there. The solar gains are still there, but it just won't leave the house as easy. And so you've got to account for that as well. That's the resilience part. Just like finding out from the client, are you planning to do any upgrades to your house? How much upgrade over what period of time? How committed are you to it? That's also about the resilience part of designing systems.
Wonderful. Thank you. All right. So we're on our last question here, folks. If I'll give it another minute afterwards for your last chance to submit questions. So go ahead. Jay just asks what the implications are of the change to the new refrigerant that will have to be used within the next year or two, and that's already mandated in some countries.
Yeah, that's a good question.
I can comment a little, Rob.
Yeah, well, other than, you're going to have to get, if you're a contractor, some new gauges and tools.
Yep.
Otherwise, it's really not that much different. There's different efficiencies, of course, and supply chain issues will be a bit of a issue at the beginning,
Yep.
But other than that, Ryan, sorry to interrupt.
No. We just did some industry engagement specifically on this with manufacturers, suppliers, and contractors. I guess the Coles Notes points are definitely cost increase to deal with the dispersion and alert technologies that are built into the equipment. So looking at anywhere between 5 to 15% is what we've heard from folks in terms of cost increases. Like this year will be a bit of a phase out of the R410A technologies, and then the bringing in the R32 and R454B technologies. And then, as Rob said, nothing really changes with the installation, but the some of the tools that are going to be required for technicians may need some updating. So there's some investments that are going to happen there. And then the last thing is the from a performance standpoint, the conventional equipment will be able to operate with more capacity and more efficiency a little bit lower, and then the cold climate stuff will get a little bit better. So there's incremental improvements, as Rob was alluding to.
Yeah, and we've been through this before, because I was around when we had the R32, and changed to R410A. The old refrigerant was, the products were still on the market for quite a while after the required change, and then R22. Yeah, when it went from R22 to R410A. Again, you had to change gauges and all that. It would be a replay of that process. It's a little disruptive for a while, and then it settles, and everybody gets used to it. The supply chain gets caught up, and prices, kind of reflect that. They'll come down.
Yeah, and for folks that are like kind of interested in getting into it, like various suppliers, Masters Group, Emco, Echo, Refrigerative Supply, if you're mindful and looking around, like they're hosting seminars in their warehouses and things specifically on this topic, so you can get some good information there, and you'll see stuff coming out in terms of webinars as well. I think we're going to touch on this subject actually when in this series in the May or something like that, Jenna.
Yeah, I think so.
Yes,
Anyways.
we are. So I'll look up the date, and folks, you'll have a link to this webinar and a follow-up email.
And then on the heating stuff, one other quick plug, April, we're doing a session on collaborating with TECA on the upcoming overheating guidelines that are going to be issued to sort of provide a bit more industry guidance on how to use F280 for those calculating for a specific refuge room than doing whole house cooling. So for folks who want to get into the sort of heat dome events and cooling protection, that session will be on that.
Yeah, perfect. So I'll put both of those links. So that last one that Ryan was talking about is on April 29th. And then what's coming in heat pump technology that I'll touch on the refrigerant is May 27th. All right, well, I'm typing this in the chat, folks. If there's another last question, we have a couple more minutes left in our session today. All right, well, I'll just put these links in the chat here. And then I can't type and speak at the same time. Oh, any HVAC blogs you can recommend? There we go. One last question.
Geez, that's a good
That
question.
HVAC Pros one.
Yeah,
We might follow up on that one, Jenna.
yeah, because
Sure.
I kind of belong to a few of them, ranging in different types of the industry, different parts of the industry. And to be honest with you, they're quick links on. I don't even know the name of them anymore because they're on my bookmarks. I just click on them. But I've found that an incredible resource. I've asked questions, answered questions, and you get extremely competent people from, there's some chats they're particularly North American, and there's some that are global. And so it's pretty fascinating, and you get real feedback about issues in the industry, mostly technical, that I belong to.
Great. So yeah, maybe Ryan or Rob, you can send me a couple links and I can include that in the follow-up email.
Sure.
So you have a chance. Perfect. All right. And with that brings us to 9:30. So thanks everyone for joining us today. I appreciate you taking some time out of your morning. Thanks as always, Rob and Ryan, for being here to impart your knowledge and wisdom. We really appreciate it. Yeah, and we'll follow up with a link to this recording along with the presentation slides early next week. And we'll see you next time.
Good
Thanks very
discussion.
much.
Thanks, folks.
Thanks, everybody.
Bye-bye.
Bye.